So I want to continue deriving the, or rather finding the inertia matrix of RBs of some common shapes. I would continue with that topic, and this time I am going to take the case of a circular cylinder. I have shown a figure on the left hand side of the screen. I have a circular cylinder, its center of mass is C. I have fixed a coordinate system as shown on the figure. C is the center of mass as usual, L is the length of the cylinder, and R is the radius of the cylinder. The task is the same: find the inertia matrix of RB at point C and relative to the shown coordinate system. In general, again I prepare myself to find the 9 scalar components, but then this body is a body of revolution, right? And thus all these 3 axes are principal axis. All off diagonal components are 0. Using planes of symmetry. What else? I will also have IC11 equals IC22. So effectively I have to perform integrations to get IC11 and IC33 only. There are only 2 independent entries in this matrix out of 9. Okay. How are we going to get IC11? We are going to use the result that I am showing on the screen right now. This is the inertia matrix of a thin disk at its center of mass. I found it, right? I'm going to use this result to find the inertia matrix of the cylinder. How do I do that? Let's have a look at this figure shown on the slide. I am focusing on a part of the cylinder. That part is a thin disk, right? A cylinder can be thought of as an assembly of thin disks stacked on top of each other. One of those thin disks, I am focusing my attention right now at one of those thin disks. That thin disk has its center of mass at C prime. Mind you, C is the center of mass of the cylinder. This thin disk has thickness dx3 thickness, and the thin disk has its center of mass at C prime, and when I try to identify the coordinates of C prime using the white coordinate system, what would be those coordinates? Those coordinates would be 0, 0, x3. Okay, so this distance is x3. That's the running variable. Eventually I will do integration with respect to x3. Okay, a thin disk having its center of mass at C prime, which is at a distance x3 from C, the center of mass of the cylinder itself. Okay. I will use this symbol DIC33 to denote what? To denote the 3-3 component of the inertia matrix of the component of the inertia matrix of the disk, thin disk. It was fine actually. Thin disk at point C and relative to the coordinate system okay. DIC33 is the 3-3 component of the inertia matrix of the thin disk at point C relative to the coordinate system, the white coordinate system. Whereas I will use the symbol DIC prime 3-3 to denote what? The 3-3 component of the inertia matrix of the thin disk at C prime and relative to I'm writing it here again. DIC prime 3-3 is the 3-3 component of the inertia matrix of the thin disk at its own center of mass, which is C prime, and relative to the coordinate system C prime, x1 prime E1, x2 prime E2, x3 prime E3. The notations are somewhat involved here. You have to pay attention, and I hope I am not making any mistake distinguishing the different coordinate systems and different centers of mass. DIC33, 3-3 component of inertia matrix of thin disk at point C and relative to this. DIC33, I'll remove this part here. We go to this point. DIC prime 3-3 is the 3-3 component of the inertia matrix of the thin disk at its own center of mass, C prime, and relative to the coordinate system fixed to its own center of mass. Right? Use parallel access theorem. I can relate DIC33 to DIC prime 3-3 plus dm, mass of the disk, right? And then x C prime 2 square x C prime 1 square, right? Coordinates of C prime disk mass is here, and I'm making some space to write coordinates of C prime measured using the coordinate system Cx1e1 that I denote as x c prime 1 comma x c prime 2 x c prime 3. Symbolically I represent it like this. Coordinates of point C prime measured using the white coordinate system. It's like this, and that would be equal to what? That would be equal to 0, 0, x3. I wrote it here also actually. Now if I use this here, what do I get? I get DIC33 DIC prime 33 plus DM XC prime 1 square XC prime 2 square. That's the parallel axis theorem. What is DIC prime 33? DIC prime 33 has to be equal to DM times R square by 2. Reference is results obtained for a thin disk. If you go back to that slide when you are reading my notes, you will find that DIC prime 33 can be written as DM times R square by 2. And what is this? This is DM times the coordinates 1 and the coordinate 1 and coordinate 2 of the center of mass. Both are 0. Both are 0 here. So these are just 0, no contribution. So DIC33 is just this much. DM R square by 2. Now what is DM? DM will be rho times dV, the volume of the thin disk. Right? I can write that as rho times what will be the volume of this disk, thin disk. It will be pi R square times dx3. Right? Pi R square times dx3 will be the volume. Thus, DIC33 is rho pi R square and then another R square by 2 dx3. Once you have this expression, IC33 for the cylinder, remember IC33 for the cylinder will be integration of DIC33 over appropriate limits, and that limit would be going from x3 equals minus L by 2 to x3 equals, maybe I go to the other side, IC33 is the full integration of DIC33 over the cylinder, and that equals rho pi r4 2 dx3, x3 going from minus L by 2 to x3 going from plus L by 2, right? As you sweep over this range, from minus L by 2 to plus L by 2, you will get the contributions of all these thin disks together. That will make the IC33 of the whole cylinder. Okay, rho pi r4 dx3. So this is going to be equal to rho pi r4 by 2 x3 going from L by 2 minus L by 2 rho pi r4 by 2 L. Rho pi r4L by 2. But then we realize that total mass of the cylinder, what is the total mass of the cylinder? If we didn't use the symbol M to denote the total mass of the cylinder, that will be rho times pi r square times L, right? And thus IC33 will be mr square by 2. mr square by 2, which happens to be the same as if this cylinder is a thin disk. As far as the component IC33 is concerned, there is really no difference between a cylinder of length L and radius R on one hand and a thin disk of radius R on the other. You both have same masses. If the mass is the same for both of them, the expression is also the same, mr square by 2. Fine. So we wanted to do integration for how many components? For IC33 and IC11. IC33 I have done already. Now I will show you the integration for IC11. We will use the parallel access theorem again. Okay, finding IC11. Finding IC11 will follow the same approach. The approach is to focus on this thin disk first, write the expression for DIC11. Once you have the expression for DIC11, you go ahead and integrate it over the whole cylinder. So DIC11, first I will write as DIC11. Let me define it. This is the 1,1 component of the inertia matrix of thin disk at the center of mass of the cylinder. That point is C. Whereas DIC prime 1,1 is the 1,1 component of the inertia matrix of the thin disk at C prime, 1 component of the inertia matrix of the thin disk at C prime. Also, I should write relative to coordinate system C, x1, e1, x2, e2, x3, e3, whereas this one is relative to coordinate system C prime, x1 prime, e1, x2 prime, e2, and x3 prime, e3. The coordinate systems are also different. So when I talk about DIC prime 1 1, I am referring to the yellow coordinate system. When I talk about DIC 1 1, no prime, then I refer to this coordinate system. Important differences as far as the concept is concerned. Again, using parallel axis theorem, I can relate DIC 1 1 with DIC prime 1 1, and then I will have an extra term here which is dm times xc prime 2 square xc prime 3 square. Okay. What is dc prime 1 1? dc prime 1 1. I am only talking about the thin disk. C prime is its own center of mass. So what is DIC prime 1 1? It again comes directly from the result that we obtained for the thin disk. This is DIC prime 1 1, mr square by 4. Of course, this m is actually the mass of the thin disk, and that distinction I will make when I write that expression here. So I will write this as dm times like this. I wrote as dm r square by 2. Here I will write that as dm r square by 4. Thin disk result. And then dm, what is xc prime 2? That is 0. You can go back and see the slide where I put that information, and this is x3. So I get 0 square plus x3 square. Okay. Again, dm will be pi r square dx3 times rho. Okay. So DIC 1 1 is rho pi r square dx3 r square by 4 plus rho pi r square dx3 to x3 square. Once we have this expression, we are going to find IC11 for the whole cylinder as integration over the whole cylinder, and that would be coming, that will have two contributions. where x3 will go again from minus L by 2 to plus L by 2, first term, and then rho pi r square x3 square dx3 going from x3 minus L by 2 to x3 plus L by 2. So, rho pi r square dx3 r square by 4 pi r square x3 square dx3. Okay, this is a straightforward integration. When you complete this integration, we should be able to arrive at the following result. IC11 will turn out to be r square by 4 plus L square by 12. That's what it turns out to be. Where M is total mass of the cylinder, that would be rho times pi r square times L. Result r square by 4 L square by 12. So if I summarize, for this cylinder, this is the center of mass, this is my working coordinate system, the full matrix. Recall, I needed only two terms, IC33 and IC11. IC33 I found earlier, now I have found IC11, and with these two quantities I am in a position to present the full matrix, inertia matrix of cylinder at C relative to so what I got here, m r square by 4 plus L square by 12 I've already convinced myself that IC11 and IC22 are same because it's a body of revolution, and then I have found IC33 as mr square by 2. And other terms are all 0. So this is a diagonal matrix. Okay. Now note that for cylinder IC33 is not equal to IC11 plus IC22. The perpendicular axis theorem is not applicable here. Why it is not applicable? Because L is not small. L is also significant. L and R are comparable, and that is why you get this result. In fact, if you can examine that if L is much less than R, then indeed the cylinder becomes a disk. We should be able to get back the result that we obtained for a thin disk earlier. We can easily examine this. If L is much less than R, this term will vanish, this term will vanish, and what do you get? You get mr square by 4 here, mr square by 4 here, mr square by 2 here. Indeed, that is exactly what we got for a thin disk. Alright, but that is true only when L is much less than R. Okay. Once derived, goes to our reference table for once and for all. Anytime future we need IC for a cylinder, we are not going to do the integration again and again. We are going to come back and refer to this result. Okay, that is. All right. Another approximation we can do with this result that we obtained for a circular cylinder. For circular cylinder, this is the matrix I derived on the previous slide. Now let's consider the case of a thin rod. Thin rod. What do you mean by thin rod? Thin rod means R is much less than L. Right? Thin disk means L is much less than R. That we have examined on the previous slide itself. Now we focus on the thin rod, by which we mean R is much less than L. What will happen? How will it simplify? It will become M times L square by 12. M L square by 12. And the third one vanishes. IC33 just vanishes. And that makes sense. If you recall, in my last lecture, I said that the physical meaning of moment of inertia is how far the mass is distributed from that particular axis. If I am talking about IC33, then IC33 is a measure of how far mass of the RB is distributed, measured from the 3 axes. Right? Now for a thin rod, what we are implying is that this dimension is extremely small, which is approximately the same as saying that the entire mass is distributed on the 3 axis itself. And thus it is expected that IC33 will vanish. That's what is happening. Okay. All right. Okay. So this is the equation with which we have been working for last several hours, if I count the lecture hours, right? Angular momentum being written as a dot product between inertia matrix and angular velocity of the body. Last class I also gave you the mathematical definition. I did not share with you the proof of how those mathematical quantities emerged, how the definitions of the inertia components emerge. I did not give you the proof. In the remaining time of this class, I am going to show that proof to you. purpose of showing this proof is to highlight an important assumption that is made while using this equation. I want to highlight that. I want to highlight the importance of that. So let's consider this body here, body M. P is a typical point on it and A is a chosen point, but A also belongs to the RB. And this A is the same A that I am talking about here. This is the frame with respect to which we want to find the angular momentum. Recall that the definition of the angular momentum of an RB about a point and with respect to frame F is this. There is an integration involved in the beginning itself. Right? Or over the whole body. Now using velocity transfer relationship, I can write velocity of point P in terms of velocity of point A right. What am I using here? I am using IF as M, or rather M as IF, and my IP is A, where A is fixed in RB. I can use this equation, can express this equation in the following manner. Of course, there is one more term here which is VPM, which is 0 because P is fixed in M. I can write VPF minus VAF in this manner, which implies this. Right? I'm going to substitute this here and now. Now I want to highlight this point. This substitution is possible only when A is fixed in the RB. And that is why I have been saying that only when A is fixed in F you can express HAF as inertia tensor dotted with angular velocity vector. If A is not fixed in the RB, you cannot get this. You cannot get this if A is not fixed in the RB. But since A is fixed, I am able to write this expression. Now there is a vector identity which is there are three vectors and you are talking about the cross product of B with C and then A with the result of the previous cross product, then this identity exists. You convert, this is a sort of conversion from a double cross product to a combination of two dot products. Now here if I take this as A, take this as B vector and take this as C vector, I can write HAF as full integration. Okay. This is HAF. It's the last expression that I wrote. The first term is simpler in the sense that the angular velocity vector on its own comes out of the integration. Recall, angular velocity vector is a characteristic of the entire RB, right? Characteristic of the entire RB. That does not change as this integration is done over as this vector RPA changes. Integration is basically done over point P. P is a typical point. When you integrate, you keep changing P to various points of the RB. But the angular velocity vector remains the same. So that is coming out of the integration. However, that is not really true here. It is not easy to pull that omega mf out of this. Okay. Now let's fix a coordinate system. There should be a point on the RB. Should not draw it outside. This is RB. Now let us fit a coordinate system here with A as the as our working coordinate system. Then RPA, if this is my working coordinate system, I can write RPA as P3, right? Because P has coordinates as x1, x2, x3 relative to the yellow coordinate system. And omega mf in general will be written as this. Okay. So now if you substitute RPA omega mf from this and this 4 and 5, 4 and 5 in 3. Okay, if you substitute these things there, you will be able to show that HAF will be IAIJ omega JEI double summation, I going from 1 to 3, J going from 1 to 3. Okay, where IAIJ components must be these, what I already showed earlier. So these will be the moments of inertia, and on the other hand you will get will be done in just 2 minutes. That's all I'll take. Or rather, I can just write it here. IA13 will be this, and same will be IA31, IA21, IA32. These definitions will fall out of the derivation I made on the previous slide. Okay, 1 1 it's 2 3 3 1 3 2. So there is a lot of algebraic steps here. I agree. I am not showing them here. Steps involved, not shown. If you want, you can make the full derivation and convince yourself that you will get what I am writing here. So this is to address the curiosity of some of the students who might be thinking about where these definitions come from. This is the direction in which you should think and derive, and you will get the answer. This is a complicated derivation because a lot of algebraic steps are here. I am not going to do this. Okay, so don't worry about it from exam point of view. But yes, if you had this curiosity, then this would help you get the right answer or the required answer. That's all. We stop here. Tomorrow we are meeting 4 to 6 Saturday. We will have tutorial session. I will solve the questions of set 5A. Set 5A has already been uploaded on Moodle. We stop.